Hey folks, this is the third lecture in the Module 3 section where we have been talking about object-oriented concepts. In the previous ones, we talked about inheritance and then we talked about polymorphism. And both of those are important concepts that you're probably going to need to understand for this one before you get here. So an abstract class is a case where we have a generic definition for something that we will later give in the details about. So we've talked about this in a couple of different ways without really actually describing it. When we were dealing with inheritance, we talked about mammals and cats and dogs and cows and all kinds of other fun mammals. And what we said was that a mammal is the top class, it's the parent class. And then a cow inherits a bunch of stuff from mammal, like it may know how to eat and how to walk and how to reproduce and whatnot. Likewise, a cat inherits all of those things, and a duck inherits all of those things if a duck is a mammal. So each of the subclasses gets a bunch of stuff from their parent. That's the idea of inheritance. And it's a very good thing because you don't want to have to keep rewriting the same exact thing over and over again. Let's take another example. If you go out and you buy a car is an instance of a vehicle. There are many different types of vehicles. So you might have motorcycle, you might have car, you might have spaceship, you might have airplane, blah, blah, blah. All those would be subclasses of vehicle. But even just taking car, there's a couple of different ways that you can use a car. You can use it as a personal car, you could use it as a taxi, you could use it as an Uber or a Lyft vehicle, you could use it as something else. So the definition of car would have a whole bunch of details in it, right? It has what color it is, what make, what model, how many doors, how many seats, how many miles per gallon does it get? Does it have any special modifications? Does it have a radio? Does it have air conditioning? All of those are things that would be attributes of the car. And it would have a bunch of methods, like it has the ability to drive, it has the ability to back up, it has the ability to entertain you with the radio, it has the ability to cool you with the air conditioner, heat you with the heat, and so on and so forth. So there'd be a bunch of methods that would be true. Then if you make an Uber or a Lyft or a taxi a subclass of car, you would still have all of those capabilities. An Uber, a Lyft, a taxi, they all know how to drive. They all know how to heat you and cool you, unless it's a terrible taxi, but that's not important. They all know how to do all of those same things that a car can do, but they also have the ability to earn some money, which is not something that a car can typically do. So you might write the parent class dealing with the car, and then you may have a subclass which deals with other things that are specific to that subclass. So the reason that we do this, and this is more of a rehash of inheritance than anything else, the reason that we do this is because it allows for us to have high quality code that we don't have to rewrite, that we've already debugged, that we can just reuse. We don't have to recreate how the car drives just because it's an Uber. That doesn't make any sense. I shouldn't have to recode all of that. Turning on the engines, having the pistons fire, bringing fuel in from the fuel pump and so on and so forth. I don't want to have to deal with all of those details. I just want for my Uber to be able to say drive, and it knows what to do. And so that's why we use inheritance. So if we go a step further from that, you've noticed in some of the examples that we've given that a car is a real thing that exists in the real world. But there are times it's useful to model things that don't actually exist in the real world or that are vague, because there's a whole bunch of subclasses that would typically inherit from them. And that's the idea of an abstract class here. An abstract class is a special kind of class where it must be inherited from, and parts of it must be overridden in the child. The child is required to override some of the methods that are presented from the parent. So, how does this all work? Well, the first thing to know about an abstract class is that you cannot instantiate it. What I mean by that is, if we go back to our example from the previous lecture where we spoke about mammals as being a class at the top, a parent, and then all the different types of mammals as being subs, or children. So then at that point, can you make a mammal? And at the time that we went through that lecture, I said it doesn't really make any sense. There is no real thing called a mammal that roams around outside. There are specific types of mammals that roam around, but mammal itself is not one. So we would say that mammal is an abstract class. It is a class that cannot be created in the real world, but it defines certain properties that are going to be true for all of its children, or all of its child classes. How do you define an abstract class? It is nothing more than putting the word abstract on front of the class definition. So if you had said class A, you now say abstract class A. Once you make it abstract, it is impossible to say my A gets new A. Because it is an abstract class, you cannot instantiate it. That is a question that is going to come up on quizzes, on tests, on interviews. If you mark a class as abstract, you cannot make objects of that class. It is not possible to make objects of an abstract class. In order for a class to be abstract, the other requirement is at least one of the methods must be abstract. How do you make a method abstract? Well, weirdly, you put the word abstract on front of the definition. Like any other class at that point, it then may have any number of attributes. They may be public or private. It may have constructors, and it may have methods. And some of the methods can be abstract, while other methods can be concrete. What do I mean by concrete? I mean that there's actually text inside of the method explaining what to do in some cases. And we're going to see an example of that here in a moment. So the main reason for doing an abstract class is to eliminate redundancy. You are putting all of the things that are true at the parent into the parent, but then you're forcing the children to override the things that are not true for them. Abstract classes cannot be instantiated. Subclasses, or concrete classes, which is what we are going to call a child of an abstract class that has all of its methods implemented, can be instantiated. So you can instantiate an Uber and you can instantiate a car, but you cannot instantiate a vehicle, even though a Uber is a child of car and car is a child of vehicle. All methods in the concrete class must have a body. What do I mean by a body? Well, after you write the header of a method, you generally have curly braces, and then you have the actual body of the method. In the case of an abstract class, you're not going to have that body there. You're just going to give the header, and then that's going to be that. No method should have an abstract reserved word in its header in a concrete class, in the subclass, effectively. Okay, so let's take an example here. So here's our UML that we've talked about before. So we have our mammal. This is obviously our parent class, and it has 4 attributes: temperature, weight, IQ, and fur color. And then we have 3 methods that are actually fully defined here. We have an eat method, we have a drink method, and we have a move method. And so the assumption here is that all of my children will be the same. They will all have the same ability to eat, the same ability to drink, and the same ability to move. As we've seen before, if any of the children need to change how that works, if a particular animal eats differently than all the other ones, they are welcome to override the eat method that they inherited from their parent. But if they don't override it, they will just call eat, and the parent's method will fire effectively. All right. But the new thing that's going on here is we now have this abstract method called make sound. And because there is one method that is abstract, this class is now abstract. So to be clear, if there is at least one method listed as abstract, then the entire class is abstract. It is because of this method, it is no longer possible to say mammal M gets new mammal, because this is now an abstract class. I'm going to go over that in a different way, and I'm going to say it a different way. People will ask, does that mean that all classes that are abstract have only methods that are abstract? That is not true. In this abstract class, we have 3 concrete methods and 1 abstract method, and that is perfectly valid. If you have at least 1 abstract method, the class is abstract. That is the only true statement. You can't convert that into other statements and memorize it a different way. It is, if you have at least 1 abstract method, the class is abstract. All right? So now we want to create a dog and a cat and a cow, our favorite animals apparently, that are all going to be children of mammal. So these arrows again imply that this is an inheritance. So dog is inheriting from mammal, or the dog is a mammal, the cat is a mammal, and the cow is a mammal. So dog extends mammal, cat extends mammal, as does cow. And we notice that there's no specific attributes listed for any of the three of these, and that means that the only attributes that they have are the ones they inherited from their parent, which, by the way, according to these minus signs, all of those were private. So the dog, the cat, nor the cow can directly change any of those attributes. To remind you, if there is a minus sign on front of an attribute or a method, it is private. If there is a plus sign on front of it, it is public. If there's a pound sign, then it's protected. So minus means these are private, therefore the dog actually has no attributes. It doesn't inherit any of these, and it has none of its own, so it has no attributes, which is a little weird, but here we are. It does have access to three methods, eat, drink, and move, and then it has an overridden method called make sound. So to be clear, in class dog, there must be a method called make sound that is an override of the make sound up here, otherwise you will get a compile error. When you have an abstract method in a parent and you try to implement the parent, you must implement the body of all abstract methods that you inherit. It is not permissible for you to not do that. So the dog, the cat, and the cow must implement make sound. They are still welcome to define other attributes and have other methods as much as they want, just like normal, but they must do that one. All right? So, as I've said before from this previous example, mammal M gets new mammal is no longer valid. You will get a compile error. The compiler will say you cannot instantiate an abstract class, or something along those lines, depending on the exact compiler. You can, however, say mammal M gets new dog, mammal M gets new cat, and mammal M gets new cow. You could also say dog D gets new dog, cat C gets new cat, and cow K gets new cow. So what's written here is polymorphism, because I have a type, which is my parent, and I'm instantiating an object of type dog, which is a child of that. Because this is a child of that, dog is a child of mammal, therefore this is polymorphism. That is allowed because of polymorphism. So all of these statements are valid, as are others like dog D gets new dog. So here's dog D gets new dog, and I can call eat on that. So what's going on here? Well, I inherited eat from above. Even though dog did not overwrite it, I am able to still call eat. And let me make that super clear. The inheritance of methods continues to work, just like it always did. Up here, eat, drink, and move are listed as public, and therefore an instance of the dog is allowed to call eat. These are concrete methods. There is actual code up here in this method that explains how to eat. Therefore, I can call it in the child. But the abstract method make sound does not have any code, therefore it must be overrode in the child, and the code must be here in the child. All right, so implementing polymorphism with an abstract class. We talked about mammal M, and on the right side we realized that we could say mammal M gets new mammal, except that's not allowed because mammals are abstract. You can say mammal M gets new dog, mammal M gets new cat, mammal M gets new cow. All of those are valid, and that is polymorphism. So the crazy part about that is we have a variable M, which is of type mammal, but I'm actually going to be able to say m.makeSound, and depending on which new I called, I actually may get meow or moo, because the different children have different overrides for make sound. So hopefully that makes sense. So in summary, there are two different kinds of classes as regarding this lecture. There are concrete classes, which is what you have written up until now, and there are abstract classes, which mean at least one of their methods is marked as abstract. The class header will have the word abstract in it, and at least one of the methods will have the word abstract in it. Abstract classes often help you facilitate polymorphism. All right, so I'm going to go through an example here. And in this example, we're going to talk about a chessboard so that it's a fairly reasonable real-life example. Live Googling a random image. What could possibly go wrong? Excellent. Okay, So hopefully you guys are familiar with what a chessboard looks like, but in case you're not, it's going to look something like that. And basically what's going on here is you have a bunch of pieces that are on an 8x8 board. So there are 8 squares across, 8 squares down. What does that sound like? Well, it should probably sound like a two-dimensional array. 8 cells across, 8 cells down. So cell 0, 0 would be here in this, I'm arbitrarily choosing which corner, but 0, 0 is going to be here. This is going to be 1, 0. This is going to be 2, 0. This is going to be 0, 1, 0, 2, 0, 3, 0, 4, and this guy is going to be 7, 7. All right, so inside of my chessboard, I have 64 squares, 8 rows, 8 columns. And on each of those squares in the beginning, this is how the chessboard is set up. These pieces at the second line are called pawns. These pieces are also pawns. It's just that this is the white player's pawns and this is the black player's pawns. And then at the back, you're going to have some other pieces. This is called a castle. This is called a knight. This is called a bishop. This is called a queen. And this is called a king. You have one king. The goal of the game is to make sure he stays protected. And the pieces have different rules. Pawns can move forward, but they can't move sideways or diagonally. Castles can move in any number of squares this way or this way, but they are not allowed to move diagonally. Bishops can move any number of squares diagonally, but are not allowed to move forward or backwards, vertically or horizontally. Knights do a weird thing. They go 2 forward and 1 right, or 2 forward and 1 left, or 2 left and 1 forward, or 2 right and 1 forward, and so on. Queens are basically allowed to do all of the above. They can go forward, they can go sideways, they can go diagonally. They just can't do the thing that the knight does. And kings can only move 1 square at a time. So pawns move 1 square. All the rest of these on the back row are able to move more than 1 square. There are other rules of chess. That's not the point of this video. I'm going to write a little bit of code that talks about how the individual pieces are allowed to move in this example. So very specifically, I'm only going to code pawns and queens. You would, if you feel like it, you guys are welcome to start writing what the other moves would look like. So we're going to start off with an abstract class, which I'm going to call game piece. And the reason that I'm doing this is because there are all these different game pieces. There are pawns, there are castles, there are knights, there are bishops, there are queens, there are kings. There's at least 6 different kinds of pieces on the board. In addition to that, there are white pieces and black pieces. So we're going to have the pieces know what color they are because that's very relevant when you're playing the game. And then they have all these rules about where they can go. So pawns are not allowed to move diagonally, except if they're taking somebody. Then they're allowed to move diagonally, but only 1 space. Generally, they're only allowed to move forward. And even that's a little bit confusing because forward for a black player means moving this way, whereas forward for a white player means moving this way. So it's important that you recognize where they are. So I'm going to make a random assumption that the board is laid out like this picture, and the black player is going to be at the top in 0, 0, and the white player is going to be down on the bottom here in rows 6 and 7. I just made that arbitrarily up, but it just helps with the coding. All right, so we have an abstract class game piece. So game pieces cannot be instantiated because there is no such piece as a game piece. There are lots of different types of pieces, but I'm going to have to write code for each one of them because they all behave differently. But all pieces have a few things in common. They all have a color, so I'm going to store that in a string. It's either going to be black or white. They all have a row and a column, which is where they're currently located. They all have a maximum movement. This is how far they're allowed to go. Pawns generally can only move 1 square, except in their opening move, in which case they can move 2. Most of the rest of the pieces can move up to 7 or 8 squares in the opposite direction, except for the king, who can only ever move 1 square. So there's all kinds of rules about that. But we're going to have to capture that, and since it's different, I'm going to go ahead and make the variable in the abstract class at the top, and then we'll just use that variable inside of each of the concrete classes. I'm going to have a Boolean as to whether they can move diagonally and a Boolean as to whether they can move backwards, because those might be useful things down the road. Okay, so my abstract class here actually has 2 constructors, and those constructors are fully built out as normal. So I have the ability to instantiate a game piece, but I can't make an object of that game piece. Huh? Okay, why would you ever have a constructor in an abstract class? Well, the reason is because it's sometimes useful to call that constructor from one of the children. I'm going to have to set all of these attributes. And I certainly can make a getter and a setter for every single one of the attributes. And indeed, that's actually what I do down below. But if you know that every game piece is going to have a specific color and a specific diagonal and a specific backwards and whatnot, it might be useful to just be able to pass all that to a constructor in one go. And then in the children, you'll be able to say base or super, depending on which language you're in, and then call that constructor. Okay, so to be clear, GamePiece is an abstract class. The reason it's abstract is because down here at the bottom, I have at least one abstract method, which I'll explain in a moment. All the other methods in here are fully built out, including the constructors. But even with constructors, I cannot instantiate this GamePiece. I cannot say in my main code, GamePiece G gets new GamePiece. And just to prove that point, I'm going to try and do it. Ignore all the rest of the code. And I'm going to attempt to execute, and you can see that I'm going to get a compile error from Java that says GamePiece is abstract, cannot be instantiated, because I marked it as abstract. And that is going to always be true of abstract classes. You cannot instantiate them. All right, cool. So back up to GamePiece, I have a bunch of attributes and I have a couple of constructors, and then I have a bunch of getters and setters. So I have getColor, which returns the string color. I have setColor, which takes in a string and sets the color. I have getRow, setRow, getColumn, setColumn, getMaxMovement, setMaxMovement, getMoveDiagonal, setMoveDiagonal, getMoveBackwards, setMoveBackwards. All of these are concrete methods. I have actually written code as normal for all of them. So public Boolean getMoveBackwards, which returns moveBackwards. All right, that is a normal method just like you've always done. But this is the new thing that you've never seen before. Public abstract Boolean can move int, new row, new column, and Boolean attack. So let me be clear as to what I'm trying to do here. I'm writing a method where I'm going to be able to call it on each piece and ask, is it legal for you to move there? Because the movement rules are very specific to each type of piece. So in the game, I'm going to have a board and it's going to have all these pieces. And if the player asks to move one piece from somewhere to somewhere else, I'm going to ask that piece, is it legal for it to be moved there? And it's then going to respond true or false. Yes, that's allowed. No, that's not allowed. If you think about this from an encapsulation standpoint, this makes a lot of sense. The pieces are different from each other. So the rules about where they're going to move and where they're not allowed to move is something that they should understand themselves. A pawn knows where it's allowed to go in my world. You could conceivably have written all these rules in the board, because you could argue that the board is the one which decides where people go, but that's not really how I think about it. In my head, the pieces are aware of where they're allowed to go. So that's a design question. You could make an argument for either side, but my design is that the pieces understand where they're allowed to go or not, and at the moment that they get moved, we're going to interrogate them and say, is that legal? Can you be moved there? And they're going to say yes or no, which is what this method is doing. So this method is marked as public abstract Boolean. So it's a public method. So when it's overridden in the child, it will be a public method. They cannot change that in the child and suddenly make it private. All of the rules about what this method does, as far as its header is concerned, are defined here and they are not changeable. There must be a method in pawn and in queen, which are going to be the two pieces that I'm going to make concrete. Each of them must have a method. It must be public. It must return a Boolean. It must take in 3 parameters where the first one is an integer, the second one's an integer, and the third one is a Boolean. That is non-negotiable because of this line in the parent. This mandates all of those rules. If I try to make an abstract class and then I try to make a subclass of it, and I make a method that does not match this, I will get a compile error that says can move is marked abstract in the parent and was not overridden in the child, therefore we are not going any further. All right? One footnote here, the names of the variables up here are irrelevant. You absolutely can change the names of the variables inside of the overridden version, but the types have to match. It has to be an int, then a Boolean. That's non-negotiable. All right? So public abstract Boolean, this is a method that's going to return a Boolean, can move, and then it has parentheses and some stuff. And then this is the really weird new thing. At the end of the method definition, there is just a semicolon. You'll notice that in every other method you've ever written, after the end of the method parentheses where you have all the parameters, you normally have curly braces and then you have your block of code. If you mark a method as abstract, you cannot have curly braces and code in there. Once you say it's abstract, you can only define the header. And very specifically, even if I just do that, this is no longer a valid piece of code. I marked it as abstract, and then I tried to put in parentheses, and it says abstract methods cannot have a body, period. Even though that body is empty, it is not allowed to have it. So on your quizzes and on your tests, when you write an abstract method, it is very important that you do not put any body in the abstract definition, just a semicolon. You also notice it highlighted it all in red once I put that in there. And of course, I cannot put in anything like return true. That absolutely is not allowed either because, again, I marked it as abstract and now I'm trying to give it a body, and that's just not allowed. So abstract methods cannot have a body. All right, so the correct version of all of this is semicolon at the end of the abstract definition. Great. So now that I've done that, I have my game piece class. It is an abstract class because of that method. For the record, I could actually not put the word abstract up here, and one of the two languages, and I don't remember which one it is, will actually be okay with that. The class is abstract no matter what, once you mark it as abstract. Okay, so this one complains game piece is not abstract and does not override abstract method can move. All right, so you have to mark it as abstract in Java. I want to say in C# it will let you not mark it, and it's okay with it because it still understands it's abstract, but don't quote me on that. Feel free to go test it because, well, there's the code in C#. If you want to go grab the C# version of it, that's the URL. I'm just working my way through the Java version. All right, so pawn. Pawn is going to be one of the types of a game piece. So my class pawn is going to extend game piece. Game piece was an abstract class. Pawn is not an abstract class. It is a concrete class. So in here, I must override can move. And as you can see, I did it right here. So as a result, this successfully compiles. If I take out this definition, if I put that into a comment like that, and I attempt to compile, it's going to say class pawn is a concrete class that inherited from game piece, which is an abstract class, and you didn't override the method can move. Pawn is not abstract and does not override abstract method can move. And that is an error, and the compiler stops. Because there's an abstract method up there in the parent, I must overwrite it here in the child. So what am I doing in this abstract method? Well, the details of all of this you're certainly welcome to go through, but I'm not going to spend 20 minutes in the video explaining all of this. But pretty much it takes in a row and a column, and it also takes in whether you're currently executing an attack, because in the case of a pawn that matters as to where you're allowed to move. It gets the piece's current row and its current column and how far the piece is allowed to move. It checks that they're not trying to walk off the edge of the board. And then it checks to see if this is the first move for the pawn, because the first move for the pawn, the maximum movement is up to 2. That's just a specific rule. And then it checks to see if you're not under attack and you're trying to change column, that's not allowed because you're not allowed to move diagonally. If your color is black and your row is less than or equal to the current row plus the max movement, then return true. So effectively what I'm saying here is wherever you currently are, plus the furthest you can possibly move, as long as you're asking to go to a row in that location, then we're good. If you likewise are a white player, then it's going the other way because you're subtracting because you're moving from row 6 to row 5 instead of moving from row 1 to row 2. All right? And so if you get through all of these if statements and you still haven't gotten to an answer, then at the very end, I return false. This is a common way to write something where you have a big complex set of rules. You're going to say, if this is true, then okay. 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 Otherwise, no. The other alternative is you do it the reverse and you say, if you're trying to do this, no. If you're trying to do this, no. If you're trying to do this, no. Otherwise, yes. So that's a common way to code something like this, where it's a big long set of if this, if this, if this. Don't try to do it all in one statement because it's just going to make your head hurt. All right, so those are the rules for a pawn. My queen is also a class that's going to extend game piece. It also has a constructor that sets it to its appropriate place, and it must have an override for can move. So every class that tries to extend their parent that is an abstract class must meet the requirements of overriding anything that was marked as abstract. Okay, and here the rules are ever so slightly different because queens can pretty much do whatever they want, so their rules are a lot simpler. And again, if you can do this or this or this or this, then true, otherwise return false. The last thing I'll talk about in here is I do have a constructor for both pawn and queen. I didn't look at it in pawn or talk about it, but effectively it takes in its color, its row, and its column, which is where it's going to be located, and then it calls super color, which is calling the constructor in the abstract class its parent, which one of those constructors that I have up there just takes in a color and sets it. And then I'm separately calling the set column, which is a method in my abstract class, and set row, which is a method in my abstract class. Those are examples of concrete methods, as opposed to this one, which is an example of in the parent, it's an example of an abstract method. All right, so now that we've done all of that, over in main, I didn't write the entirety of chess. There's a whole lot of rules that you would have to write, but I wanted to give you just kind of the start of how you would do this. So I started off and I created a board, and that board is going to be a two-dimensional array of game pieces. And note that I'm specifying it's of game pieces. It's not a two-dimensional array of pawns or a two-dimensional of queens. This is because I'm going to need polymorphism here, because I need the board to be able to take any kind of game piece in each of the squares, because there can be a queen in there, or there could be a king in there, or there could be a pawn in there, or a bishop or a knight or whatever. So game piece board gets new game piece 8-8, which is because it's an 8-cell by 8-cell board. And then I'm going to create the black queen and the white queen. So board at position 0-3, row 0, which is the back row, the very top of the board, position 3, which is the 4th cell, is going to get a new queen, and that queen's going to be black, and her position is going to be 0-3. And then likewise, board 7-3, which is all the way down at the bottom, is going to get a new queen, which is white, and that's going to be also in position 7-3. So now let's take a look at all the black pawns that we need to make. So rather than instantiating them one at a time, I just used a little loop because it's easier than writing 8 statements. So I said for I equals 0, I less than 8i plus plus, board at position 1, which is the second row, because again, row 0, row 1, at position I is going to get a new pawn, and it's going to be black, and its position is going to be 1, I. And then making all the white ones is pretty much the same. I could have done this all in one loop. I'm just breaking it out so that you can see it. Wow, that's supposed to say white in that case. All right. And let me fix that in both of the languages, because that would be bad if you guys get confused by that. So, yep, those are supposed to be white pawns. I made all the pawns black. Oops. All right. And so now, just to prove a point, I'm going to check to see if a particular piece can move somewhere. So I'm going to pick an arbitrary pawn. This is called a queen's pawn. It's the pawn directly on front of the black queen. So I'm asking if board at position I3 can move to position 2-3 and it's not an attack, this will return yes or no. And so when I run this code, now that I've undone all the things that I did to break it earlier, we're going to see the black queen's pawn can move 1 forward. So that is a valid move. That returned true. And just to prove a point, what happens if I try to move the pawn sideways, which is not a valid move? So instead of it moving from 1-3 to 2-3, which is forward 1, I'm going to try moving it from 1-3 to 1-4, which is going to be 1 to its right. And in that case, you can see moving to the right is not a legal move. So obviously, there's a lot more code to write here if you were actually going to make a fully functioning chess game, but hopefully this gives you guys the idea of why you might have an abstract class, why you might want to instantiate that class, how you would go about using all the methods. This also demonstrates polymorphism because the board is polymorphic. The board is of type game piece as opposed to being of type pawn or of type queen, because that's what you need it to be. And I think this is a pretty cool little example. The code for Java is here. Again, if you want to play with it, click here and hit fork. And the code for C# is here. and they are identical. They do the same thing, so you guys are welcome to look through them. They're pretty much the same, except for the syntax being ever so slightly different. So hopefully that explains abstract classes really clearly, and this will absolutely be on quizzes and tests. You definitely need to understand how to write an abstract class and how to use an abstract class in the world. Next video is going to talk about interfaces, which are similar but different. See you then.